All right, today we're going to talk about three different types of limits and how to calculate them. Remember, limit is nothing more than finding what does the y value approach as x is getting close to a number that we're interested in. The first type that we're going to look at today are ones where we can do a straight substitution because there's no 0 over 0 situation that we could have. So our first type would involve limits where we can do a straight substitution. So if we're taking the limit as x approaches 3 of 5x plus 1, well, 5x plus 1 is a polynomial. It's a line. It's linear. We can directly substitute the 3 in. This particular limit turns out to equal the number 16 because 5 times 3 plus 1 is 16. There's no danger of getting into a mathematically sensitive place like 0 over 0 from following the points on a line. The only places we're going to have to be really careful of is if we happen to see rational functions. But even this rational function, the limit of the function 5 over x minus 4 as x approaches 2. All right. Sure, this function does have some places that cause us concerns, but 2 is not one of them. We can simply plug in 2. My denominator becomes negative 2, which is super great for us. So this particular limit would be negative 5 halves. All right. Now, if in this same function we were looking at the limit as x approached 4, then we'd have the situation of 5 over 0, and we would need to take a look at points just to the left and to the right of 4 and see what my function values are approaching. So that's the first type, straight substitution. If we have a polynomial, we can just plug the number in. This could be x squared minus 5x plus 3, any sort of a polynomial function. Remember, polynomial functions are functions where the exponents are non-negative integers. So they're 1, 2, 3, 4, 5. We don't have any exponents that are fractions. We don't have any exponents that are negative integers. Moving on to the second type. The type where we can factor out a common term. So the limit of the function x squared minus 3x over x as x approaches 0. Here we can't plug in 0 because if we did, we'd have 0 over 0, what's called indeterminate form, something that doesn't mean anything at all. So we're going to take the rational function and try and find another way to express it. So as I'm looking at this limit, I'm going to take the numerator and factor out a common x. Another way to write x squared minus 3x is to write it as x times x minus 3. Now we have everything broken down into factors. The numerator is all factors. It has x as a factor and x minus 3, and the denominator is a factor. When we have factors, we can simplify fractions. X over x is just another name for the number 1. So this simplifies down to x minus 3 and so calculating the limit of x squared minus 3x over x is the same as calculating the limit of x minus 3 as x approaches 0. And that limit would turn out to be, Gabby? Good. We'll see how this one works since I just made it up off the top of my head. You can see there's not much up there, so there may not be much to this problem. With this function, x squared plus 6x plus 8 over x plus 4, analyzing it as x approaches negative 4, we're not able to put negative 4 into the problem because if we do, the denominator is definitely 0. And the numerator, I get 16 plus negative 24 plus 8. That's also 0. Now, it really didn't matter whether the numerator was 0 or not, but generally, we want to see the 0 over 0. Because if we do, that means there's a way to cancel this x plus 4 out of things for us. Yes, Rachel? What would 0 over 4 be, anyone? 0 over 4 would be 0, so that would be that's a number that we can actually approach. But something like 5 over 0, that's not a number, so that's something we cannot approach. Very good question. So again, when I put in negative 4, I ended up with 0 over 0. And anytime we get 0 over 0 like this with algebraic expressions, that means the top one's probably going to factor so that that x plus 4 is going to reduce with an x plus 4 in the numerator. So in a way, we have a little bit of a chance to, and the calibration's off a little bit, it appears. We have a chance to cheat a little bit. We're really hoping that we see an x plus 4 up there. So that helps us in our factoring in terms of what the other factor needs to be to cause us to have x plus 4. Let's see, at the end, how can I get 8? 4 times 2. The way to get the x squared at the front, x times x. And we just need to figure a sign here. Since it's a positive 8, it needs to be a positive 2. Yes, CJ? Yeah, x is approaching, so no, we're just seeing what are the y values for this equation as our x value gets closer and closer to negative 4. It'd be a lot like being on a roller coaster and say there's a number line under our roller coaster. As we get closer to the number 12, what's our height on that roller coaster? Right? Because as my x increases, I have different heights as I'm going around. So that's what we're looking at here. So we're letting one variable change and seeing what is the other variable getting closer to. I couldn't hear. Yeah, here x approaches 0. I can plug in the 0 like we did on the regular straight substitution, and so we end up with negative 3. So this particular type of factoring out a common term, notice what happens on these. After we factor out that common term, it turns out to be a limit that's the previous type that we already know how to do. And when we solve equations, that's basically what we're doing with equations. The easiest equation to solve is it says x equals 5. What does x have to be to make that true? 5. Now if I have 2x equals 10, what does x have to be? The first thing we do is divide both sides by 2, and now we get that x equals 5, and it's again the simpler level. So algebra is nothing more than taking something and reducing it down to simpler forms. And the book that algebra is based upon, or the concepts of algebra is based upon, its translation is basically reduction and simplification. So as you take something complicated, like we took x squared plus 6x plus 8, we reduced it to this, and that allowed us to simplify the expression down. What is this limit, by the way? Negative 2. We're finding, no, as x gets closer to negative 4, we have the graph of this function, and as we're writing the graph, and we get closer to x equals negative 4, our y value is getting closer to negative 2. And the thing with limits is our y value could approach a number even though the function doesn't actually equal that number at negative 4. In this case, at negative 4, it doesn't exist. Because if we plug negative 4 in here, we get 0 over 0. This one is one of those cases where it turns out to be a hole in the function. And from the curriculum in IB, you don't need to worry about the fact that it's a hole, where AP does need to know what kind of discontinuity is. Yes, ma'am. Okay, let's do that. If we put -4 in here, I get 16. If I put -4 in here, 6 times -4 is -24, and plus 8. Well, 16 plus 8 is 24. Minus 24 is 0, so I get 0 in the numerator. And if I put -4 in there, I get 0 in the denominator. So we can look and try to do that, but what happens is we get 0 over 0. Usually we know we're going to have to factor if our denominator becomes a 0. That's one of the things we're going to have to do. Yeah. I'm not quite understanding what you're asking. Probably, yeah. There are since they're building things up for you to practice ideas. Now, there are functions where, if I made that 7x, it's still undefined at 0. Now, the question would be, if that's 7x, what's actually happening to the left and to the right of 0? And that'll be something that we look at in the next section. And it'll probably be a situation of where we're not going to have a hole there, but it's going to be like the 1 over x graphs, where we're going to have vertical asymptotes. By the way, with the recording like this, you don't see things like, the idea of vertical asymptotes and me pointing at things. Yes, Jacob. If it comes out 0 over 0, that's usually a big time hint that the numerator is going to factor in such a way that the factor that's causing us problems, in this case x plus 4, is going to reduce out to a 1 and leave us with a part or a piece that's not a bothersome. If we get 0 over 0, right now I'm hard pressed to think of any time where it's not going to be non-factorable. But, in mathematics you never say never, because there's so many different possibilities. And so, by the way, by looking at seeing what it reduced to, x plus 2, the graph of this is going to be similar to the graph of this. The graph of x plus 2 is just a line that passes through 2 with a slope of 1. This graph is almost the same thing, except it has a tiny little hole there at -4, right, which our graphing calculators don't demonstrate to us. Now, the last kind that we're going to look at is going to be ones that we're definitely not going to be able to plug it in place. We're going to let x approach infinity. As x gets larger and larger and larger, what's happening to the y value for our given function? Right? Now, here's the thing to remember. See if I write this correctly. For x's that are bigger than 1, so for positive x's, all right? Greater than 0. Yeah, I wrote one thing and said the other. Thank you for catching that. All right, x is always going to be less than x squared. If you pick any number bigger than 0 and square it, I better change that to greater than 1, shouldn't I? Because a half squared is 1/4. Was Gabby ahead of the game here? For x is bigger than 1. Okay. For any x that's bigger than 1. Yeah, that's going to work now. If you take any number bigger than 1 and square it, it's going to be bigger than your original, like 3. 3 squared is 9, bigger than 3. And by the way, that original x is bigger than 1, so we can stretch the inequality out to this side. 1 is smaller than x, and that x is going to be smaller than x squared. And guess what? That x squared is going to be smaller than x cubed. And that would continue on, that relationship. So x to the fifth is going to be bigger than x to the fourth, be smaller than x to the sixth. So that lets us look at some limits of real basic things. So the limit of 1 over x as x approaches infinity. All right. 1 is always going to be smaller than x. So we're going to have a value of 1 that's always smaller than a value that's growing. So I'm going to have 1 over 10, 1 over 1,000, 1 over a million, 1 over 10 million. What is my y getting closer to as I let that x get larger and larger? Yes, 0. Mm-hmm. As x gets larger here, approaches positive infinity, my y value is getting smaller and smaller. 1 over 1,000, 1 over a million, 1 over 10 million. It approaches 0, it doesn't get to 0. And because of this relationship between the squares and the cubes, let's make that infinity, we can extend the idea. All right. X squared over x cubed, the limit of that as x approaches infinity, is also going to be 0 because that x cubed is going to get bigger faster than the x squared does. And we could actually simplify that down as well if we'd like. Yeah. X over x squared, that limit would also be 0. Yep. Because here the denominator is getting bigger much faster than the numerator. Yes, ma'am. Okay. Could it be x over x cubed, she's asking? It's still yeah, x cubed is definitely bigger than x squared, and x squared is bigger than x, so yeah. It's the smaller exponent, yeah. Yes, Gabby. Uh, what do you think the other answer is? It could be awfully wrong. Actually, there are a lot of different answers as x approaches infinity. With our reciprocal function, 1 over x, this first one, yeah, x is definitely approaching 0. But if I take that same function, 1 over x, and change it to 1 over x plus 3, remember that plus 3, the effect of that on the function is going to take the whole function and move it up 3. So it's going to approach 3. So instead of the x-axis being our horizontal asymptote, it's going to approach 3. And then on this side, it's going to approach 3 that way. So that would make the need for a longer chord. But that would make it so there's more than 2. There's, all we have to do is add a different value. And there's even a place where the limit would not exist. Okay, if we think of the x cubed function. If we think about the graph of the x cubed function, the x cubed function looks like that. And so if we look at just that function in and of itself, as x approaches infinity, y keeps growing. So it doesn't have a limit. It grows without bound. But we're not going to look at polynomial functions like that. We're going to look at some rational functions. So let's take this forward and look at a situation like some of ones that they had in what you were supposed to read last night. So we're going to look at the limit of this function as x approaches infinity of 3x minus 4 over x plus 2. Now obviously we can't put in infinity and do the arithmetic. What's 3 times infinity minus 4 divided by infinity plus 2? We could find different values, put in 100, put in 1,000, put in 1,000,000, get answers and get an idea of what's happening. But what we're going to do in this case is we're going to take whatever the greatest power of x is. In this case, it's x to the first power. And we're going to divide every term up here by that x. So basically, I'm going to take the 3x divided by the x, the 4 divided by the x divided by the x, and the 2 divided by x. Mathematically, we're basically multiplying the numerator and denominator by 1 over x, which is the same thing as dividing everything by x. Multiplying by 1 over x matches dividing by x. Now, what's another name for 3x over x? 3. What's another name for x over x? 1. 2 over x and 4 over x don't have other names. But yet we can analyze what happens to them individually as x gets larger and larger. So if we consider our limit in this form, what's that, 2 over x? Now we can analyze the pieces. What is 4 over x going to approach as x gets larger and larger? Just this little term right here. 0. So my numerator is going to approach 3 minus 0. So my numerator is going to become 3. And my denominator, as x gets bigger and bigger and bigger, it's getting close to being the expression 1 plus 0. Okay, x is getting huge. So 2 over a very huge number is going to be pretty darn close to 0. And 1 plus something very close to 0 is going to be 1. So we're using this property of the limit. As long as the denominator has the larger power, we know that that's going to be 0. And last night I asked you to read through and find the different properties there. And there were properties listed about taking the property of a sum, taking the property of a multiplication, I think, property of the limit of a constant, limit of a sum. So the limit of this function turns out to be 3. It's probably a good time to talk about those properties. We're going to let x approach some arbitrary number a. If our function is just simply the constant function c, where there is no x involved in a function, the limit is always going to be c. So like back on the previous one, when I'm taking the limit of the top, I'm really taking the limit of 3. But what is 3 going to approach as x approaches infinity? Well, 3 is going to stay 3. It doesn't have an x in it. It's not changed by x's actions. The next one is if we have a function multiplied by a c, like 5x or 3x squared. This is equivalent to taking c and multiplying it by whatever the limit of that particular function turned out to be. So if I want the limit of 5x, it's the same as taking 5 times the limit of x. There are places where these little tricks about limits are going to be helpful to us. What's the next one say? I think it's a plus or minus 1, isn't it? If I'm taking the limit of two functions that are being either added or subtracted, that's the equivalent of taking the limit of the first function and adding or subtracting it to the limit of the second function. And back on the previous page is where we actually applied that. So I kind of put the cart before the horse in a way. Let me go back to the previous page. I'll come back there. Here when I'm taking the limit, here is the addition of two functions. 3 is a function and 4 over x is. So basically, we looked at the limit of 3. That's 3. Then we looked at the limit of 4 over x as x approaches infinity. That was 0. And then we took the 3 minus the 0, and that's how we ended up with that 3. So we were actually applying that function when we were doing this limit here, without really knowing that we were allowed to do that. The same thing happened in the denominator. I have two functions added together, 1 and 2 over x. So taking the limit of both of those pieces independently and then adding them. And that also had that first property. The limit of 1 as x gets bigger and bigger is going to be 1. Yes, Jeremy? There, that piece would be infinity. So that's part of the reason why we're dividing by x, so that we don't have this 3x that we can't deal with. Now we have a 3 and a 4 over x that we can deal with. Rachel? Okay, well 3 times 4 over x would be the same thing as 12 over x, which would still be 0. Yeah, because 12 over x is going to approach 0, but just a little bit slower than 4 over x does. Oh, if that's a multiplication up there? Yeah. It would best just be 0, yeah. Let me come back to this page and add the property that she's talking about. If we take the limit as x approaches a number of a product of two functions, that's the same thing as taking the limit of the first function times the limit of the second function. X approaches infinity, or a. Let's erase that and make that an a for you. And have to erase more. And there, it's times. When you watch the video, are you going to ask the same question? All right, so like if we had our function was x plus 2 times x plus 5, we don't have to multiply it out to calculate the limit. We could just take the limit of whatever x plus 2 is times the limit of the x plus 5 factor. We don't have to worry about multiplying. Now, x plus 2 times x plus 5 is something simple for us to multiply. Imagine those two terms were like x squared minus 5x plus 4, and then the other one's x squared plus 8x plus 13. Things we definitely don't want to multiply. And then the last one, if we have multiply, we also have to talk about the possibility of dividing two functions, which is pretty much what we had in that example that's on the other page. F of x over g of x. It's going to equal the limit of f of x divided by the limit as x approaches a of g of x, but with one caution. What's the one caution we have to place here? Yeah. Yeah. The limit as x approaches a of g of x better not be 0, because then we'd end up in the 0 situation. We dial 1-800 Mr. Swift or something like that and go from there. I could have that, because I have MR, S, and then 4 digits WIFT. Wow. I can make my own infomercials. Huh. I can make some money. Okay, thank you, Mariah. That sound you hear, Mariah, is your grade going down. We're going to find out how much this picks up. All right, let's look at this one now. So let's find the limit of this function. I just made it up. I have no idea what the graph of this function looks like, but yeah, I can see what happens to this function as x approaches infinity. I know how to do everything. I just don't know. So I can find out what this graph is going to, how it's going to be behaving as x approaches infinity. All right, so remember what I told you to do in these situations? What should I divide everything by? What should I divide everything by here? Divide everything by x cubed in this case. So we're going to rethink this as x approaches infinity. Now there's two ways of thought in terms of how to write this. Some people like to take the expression and simplify it down before they tack the limit on with it. I'm somebody that was taught to start out with the limit and then just keep the limit as you go through. As long as you're clear in what you're doing, don't start out by writing this and then suddenly leave off the limit symbol and then bring it back in at the end. If you start with it, keep it. Or if you start with it, then over on the side, you can do some simplification work and then bring it back up in. From what I've seen so far, it's part of showing your work, and as long as your work is clear and they can see where stuff is. Now, some of you work in what we call the circular method. You've got stuff all over in a circle, and then some of you are chaos method, where things are everywhere. What would I get if I take the first term divided by x squared? 3 over x. What would I get if I take the second term divided by x squared? 2 over x squared. I'm dividing by x cubed, by the way. I caught that before Gabby did. And if I divide the third term by x cubed, 1 over x cubed. So we're breaking it down into pieces that are manageable. You might think, boy, this looks worse, but it is manageable. What's x cubed divided by x cubed? 1. And what's 4 divided by x cubed? 4 over x cubed. Each of these pieces, we know their behavior as x gets larger. As x gets larger, what happens to 3 over x? It approaches 0. As x gets larger, what happens to 2 over x squared? It approaches 0. So here we're using that addition property that allows us to add the individual limits of functions together. As x gets larger, what happens to 1 over x cubed? It approaches 0. 1, what does 1 approach as x gets larger? 1. 1 doesn't care what x is. It's going to stay 1. What's 4 over x cubed going to approach as x gets bigger? 0. If I simplify all this out, I have 0 over 1, also known as 0. So I don't know the behavior of this function in a lot of places, but I do know the graph of it. When I get clear out here towards infinity, it's going to be approaching 0. Jeremy? It would be like this. You're not going to be able to shorten this down to anything. Now, on tonight's work, you're going to, like on the substitution ones, you write down what it says, put the value in, and just write down the answer. The algebraic ones and this ones, you're going to have to show a little bit more. Here, you can shorten some of this up in here. There's a couple things you can kind of go from one point to another. Like I could go from here directly to 0 over 1. Now, the question would be here, what happens as we approach negative infinity? It gets a little bit different. This is still going to be 0, right? But it's going to be the underside of 0. It's going to be a very small negative. This one's going to be a positive, because x squared is always going to be positive. So now we have to consider the effect of the negatives versus the positives. Am I going to have a positive so far or a negative? And this one's going to turn out to be a positive as well. cube the negative, I get a negative, but then subtract it. So I don't know whether my overall numerator is going to be positive or negative. I just know it's going to be close to 0. Same thing in the denominator. Well, my denominator is going to be positive because a negative cubed is a negative. And then subtracting a negative makes a positive. So I've got a positive on the bottom. I'm not entirely certain about the top, whether it's positive or negative. My guess is it's probably negative because this is a greater number. When I start to square something, it makes them very much smaller. And if I had to hazard a guess, I would say on this end, it's going to approach like that. And then part of calculus is to find out what else it does in between. Sometimes this denominator is going to equal 0, right? What would x have to be to make that denominator 0? What number when I cube it gives me 4? What number when I cube it gives me 4? Sure, but there's still a way we can say it, not necessarily read off a decimal. The cube root of 4. When I take the cube root of 4 and cube it, I get 4. That's why we often leave things in exact form as opposed to changing them to decimal. So the cube root of 4. This evening, or this weekend, what I'd like you to do are questions 1, 2, and 3 from 15a. 16a, yeah. You guys want to get out of that probability. So 16a, 1 through 3. Now, number 1 is all just straight substitutions. So since I know you're going to be writing elsewhere, number 1, you can just write down like a, put down the number since we already know what the limit is going to be, what the expression is. But on number 2 and number 3, on number 2, you're going to have to pull out factors. You're going to have to show me something there instead of just writing down only what the number is. And then on number 3, you're going to be approaching infinity. So at least show me the rewritten form of the polynomials as we go there.